Hello, today this is section 9-6. We're going to be working with the ratio test and the root test. My favorite test to use is the ratio test, and it is used most frequently on the AP exam. So this is one that, highlight this right here, this is absolutely one that you should know. Now, ratio test, try this if a sub n contains factors such as n factorial or x to the n. That's how you know that that would be a good test to try. Okay, so for this series, a sub n as the summation as n goes from 1 to infinity, I have the limit as n goes to infinity of the absolute value of the next term, written as a sub n plus 1 divided by a sub n equal to L. Now, depending on what L is, if L is less than 1, we know that the series is going to converge absolutely. And again, absolutely just means it's guaranteed to be convergent. It's the stronger type of convergence. Okay, but a lot of times we'll just say that it converges. If L is greater than 1, or if L is infinity, then the series will diverge. And if L is equal to 1, the test is inconclusive and you must try another test. So we're going to try to avoid that one. Okay, so looking at number 1, I have the summation as n goes from 1 to infinity of 5 to the nth over n factorial. Now, since I see that n factorial, that's my clue. Hey, I want to use the ratio test. So I'm going to write out my ratio, the limit of the absolute value of the next term. So that's going to be to the n plus 1 term. And that would be 5 to the n plus 1 all over n plus 1 factorial divided by 5 to the n all over n factorial. So there's my ratio. Well, we all know that when we divide by a fraction that we're going to have to multiply by its reciprocal. So I'm going to write that as the limit as n goes to infinity as 5 to the n plus 1 all over n plus 1 factorial times n factorial all over 5 to the n. Okay, so from here we have to think about how do we reduce these. So I'm going to kind of see if I can squeeze this up here. I would have the limit as n goes to infinity. Let me get rid of that because that's going to be in my way. The limit, oh, just a minute. We'll do a new color so you know that I've changed it. The limit as n goes to infinity. I'm going to write this 5 to the n times 5 to the 1. So you realize that that's really 5 to the n plus 1. Down in the denominator, when I have my n plus 1 factorial, isn't that the same as n plus 1 times, and I'll subtract 1 from that, that would be n factorial. And then I multiply that by n factorial all over 5 to the n. Well, I can see that this 5 to the n is going to cancel out with that 5 to the n, and that n factorial will cancel out with that n factorial. So what I really have then is the limit as n goes to infinity of 5 all over n plus 1. Well, if I plug in infinity to that, I can see that that goes to 0. So my question is 0 less than 1? Yes, it is. So we know it's going to converge absolutely. Okay. Now I'm going to skip to number 3. I'm going to skip some problems here and then just have you do them all at the end with in partners so we can get through all of our notes first, and then you can just work on some extra problems at the end. Number 3, I have the summation of n going from 1 to infinity of 1 over n to the 4th. Well, if I look at that, I have 1 over n to the 4th. Now think about our series that tests that we've already done up until now. Sure, I could probably do a ratio, but if I look at that, isn't that a p series? Where p is equal to 4, which means it's greater than 1. So that really converges right there, and I don't have to do anything else. So be smart about your problems today and just be looking at different series that we've already had. Now I just want to show you that if in fact, if I did say I was in ratio mode and wanted to do the ratio, the limit as n goes to infinity of 1 over, and that would be n plus 1 to the fourth, all over 1 over n to the fourth. What I would get there would be the limit as n goes to infinity, and that would be absolute value around that, by the way. But it really doesn't matter since it's raised to the fourth power, and that's really why I didn't put it in the first time. I have n to the fourth over n plus 1 to the fourth. Well, we see what we have the same degree in the numerator and denominator, and so what I would get would just be 1. Well, if you look up in the box, if this value here is equal to 1, it's inconclusive, and you have to try another test. So it's very helpful that you identify these right here first and see that it's a p-series, and then that saves you a lot of time. Okay, so let's do another one. Let's try number 4. I'm looking at that and I see that I have a 3 to the n there. So I am going to again try my I'm going to try my ratio test. So if I look at, first of all, if you want to skip that first step where you're actually showing the ratio and just go straight to showing me that the limit as n goes to infinity of my next term, which would be n plus 1 squared times 2 to the n plus 1 plus 1, I'm going to go ahead and write n plus 2 all over 3 to the n plus 1. Multiply that times the reciprocal, 3 to the n, all over n squared times 2 to the n plus 1. I can look at that and see, oh, this doesn't look very nice. I really should have absolute values around it, but I don't think I'm going to really need it. So I just need to start working on simplifying. Okay, so I'm going to write this out for you. The limit as n goes to infinity. I have n plus 1 squared, 2 to the n, 2 squared, 3 to the n. In the denominator, this is really 3 to the n times 3 to the first times n squared. And then I'm going to write that 2 to the n times 2. I'm just splitting up those exponents just so that it's easier to show how I'm actually reducing. And this is a step you really wouldn't have to show. Okay, so this 2 to the n right here, that's supposed to be a 2 to the n, is canceling out with that 2 to the n. I have a 3 to the n canceling out with that 3 to the n. And I get this 2 right here, I'm going to cancel out with that exponent. So when I look at my final answer here, I have the limit as n goes to infinity. It looks like I have a 2/3, and then I have an n plus 1 all over, oh, that's quantity squared, over n squared. Well, we know if we plug into this part of my fraction, that limit's just going to go to 1 because I have the coefficient of n squared over the coefficient of n squared. So that's just going to be a 1. So my final answer here is just 2/3. Since that is less than 1, we're going to say that that converges absolutely. Okay. Moving on to the next box, I have a root test. The root test, notice right here, used infrequently on the AP exam. And I always just like to point that out, that this is very rarely used, but hey, we'll go through it anyway because we just need to make sure we have all of our tests here. But once again, the ratio test is the one that's used the most. Looking at this one, it says for the series, the summation is n goes from 1 to infinity of a sub n. Find the limit of the, to solve that, we find the limit of the absolute value of the nth root of a sub n. And we find out what that is, our L value. If it's less than 1, then the series converges absolutely. I'm just reading the box here. If L is greater than 1, or if L is infinite, then the series diverges. And once again, if L is equal to 1, we picked the wrong test basically. The test is inconclusive and we need to find another test. Okay, so looking at number 5. I have, oh, this thing driving me nuts today. There we go. I have the summation n going from 1 to infinity, e to the 3n divided by n to the nth. So what I'm going to do is, since I have n to the nth, I'm going to do the limit as n goes to infinity of the nth root of e to the 3n all over n to the nth. Okay? So basically I'm just taking the nth root of everything. Now if you need to, I don't know if you need to rewrite this just so you understand, this is really e to the third all over n, all of that to the nth power. That's what I really have inside that radical. So when I take the nth root of something raised to the nth power, what I get is just my e to the third over n. The numerator is just a constant. So this limit is equal to 0, which happens to be less than 1. So therefore, this series converges absolutely. Okay. Okay, so this is the plan now for the rest of the period. Is I want you and your partners or in your groups to work with together and do numbers 2. I do believe we skipped number 2, didn't we? Yep. I'd like you to do number 2 and number 6. And those are basically going to be, obviously number 2 is going to be probably the ratio test. And number 6 is probably going to be the root test. And then what I have on this next page, 7 through 12, I've got some things kind of mixed up. So you can use a variety of different tests on these right here, and I'd like for you to practice those. I'm going to go ahead and write out my solutions here, so I want you to stop the video, and I'm going to write out my solutions so you can check them at the end of the period. I will also leave the answer key with the sub if you just want to, when you get done, maybe it's more time effective or time efficient too. When you get done with these, just have one person from your group check with the sub to see if you got numbers 2 correct in numbers 7 through 12. And then you can go ahead and start working problems from your textbook. Okay, I went ahead and wrote in all my answers here. So you can take the time here if you want to compare what you got. For number 2, I got an answer that it diverges, and I used the ratio test there. And again, slow this down if you need to see it a little bit slower. Number 6, I did the ratio test and I got it to converge absolutely. Then on the second page here, number 7, I found it to diverge by the nth term test. Number 8, I got, hopefully you noticed that that one was geometric, and that was going to converge. Number 9, talking about number 9 here, I actually did the integral test, and I got that to converge. Number 10, I did the limit comparison test, and I got that to diverge. Number 11, I did the ratio test, and that series is diverging, showing all my work there. There it is in purple on the left. And then in green on the right, it's alternating, so I knew that it was converging. Sometimes they will ask you to classify the convergence, whether it be absolute or conditional. They don't always ask you to do that. So if they're not asking you to classify them, you really don't have to say that it converges conditionally or absolutely. But right here, I went ahead and showed that with the alternating series tests, I knew that it would converge, but when I did the absolute value, I saw that it was diverging. So by the direct comparison test, I found that that absolute value of the series would diverge. Therefore, the series converges, but it converges conditionally. So let me kind of go back up, scroll up a little bit more on the green. There's my work for the alternating series part, but then I double checked the absolute value of that series and I got it to diverge. Therefore, that series is going to converge conditionally. Okay, so there you go. That's all the notes for section 9.6. Have a great day.